Hello, my name is Andreja Kudelić. Today, I will present the results of a research on reconstructing the incrustation technique, a post-firing method used to decorate prehistoric pottery in Croatia. The white paste inlay, or incrustation, is a distinctive and widespread pottery decoration technique, particularly popular within the Carpathian Basin. It involves applying a white paste into engraved motifs, creating striking contrast against dark pottery surfaces. In Croatia, this long-standing tradition began in the Middle Neolithic and continued through the late. However, it became most prominent during the Copper Age, especially in the Kostolac and Vucedol cultures. It is also characteristic but less prevalent in the Bronze Age, especially for the Pannonian complex of encrusted pottery, and it's less common during the early and the late Bronze Age. Initially, research on this technique focused mainly on stylistic aspects. However, recent advancements in analytical methods have shifted attention to its production process and material composition. Studies across Europe reveal regional variation in raw materials. In northern Italy, inlays were typically made from talc and bone powder, while in the Carpathian Basin, inlays was composed of calcite, hydroxyapatite from bones, and aragonite from mollusk shells. It has been observed that mollusk shells were predominantly used in the Copper Age, while bone became more common in the Bronze Age. While it is assumed that raw materials were burned, ground, and mixed with binders, the exact method of homogenizing the paste and applying the inlay remains unclear. Experimental research has yet to confirm how the binder functioned and how the inlays was fixed. To better understand how the white paste inlay was made and applied, this study focused on three main objectives: to analyze the composition of late Copper and Bronze Age inlays to identify the raw material used, to reconstruct the manufacturing and application process by testing hypotheses about binding materials, challenging the idea of organic or clay-based binders, and instead proposing lime and bone-based plaster techniques. Finally, the goal is to propose a recipe, production technique, and application method, all supported by analytical methods and archaeological experiment. This study is the first to take an integrated approach combining controlled and real conditions, with materials identified through X-ray diffraction, infrared spectroscopy, and thin-section microscopy on Copper and Bronze Age pottery from Croatia. To determine the raw material used for inlays, 20 decorated vessel samples were examined, 10 from late Copper Age and 10 from early and Middle Bronze Age. These samples came from 8 archaeological sites across Croatia. Complementary analytical methods were applied: X-ray diffraction to identify crystalline structures, infrared spectroscopy for microstructural components, and optical microscopy for texture analysis. The analytical method confirmed the presence of hydroxyapatite, calcite, and aragonite in the inlays. The bone-based inlays display phosphate and carbonate absorption bonds, with some samples indicating complete calcination. Inlays with strong carbonate signals contain calcite, while aragonite peaks confirmed mollusk shell origin. Thin-section microscopy further supported these findings, revealing distinct differences in composition and texture between Copper and Bronze Age inlays. Copper Age inlay were composed of fine-grained carbonate paste with characteristic mollusk shell fragments, while Bronze Age inlays contained poorly sorted bone fragments with fibrous microstructures and occasional mineral inclusions. These findings confirm that Copper Age inlays were produced from burned and powdered bone and mollusk shell, while Bronze Age potters primarily used bone material. Despite these insights, several key questions remain unanswered. How was the white paste prepared and applied to pottery? what firing conditions and duration were needed to process the raw material and achieve desired properties. How was the paste homogenized and what type of binding agent ensured its durability and adhesion? To address these questions, we propose that potters use lime and bone-based plaster rather than organic or clay-based binders. Bones are composed of bioapatite and transform into hydroxyapatite by firing above 700 degrees. Mollusk shells are composed of aragonite and decompose into calcite by firing above 450 degrees. Heating calcite further to 700 or 800 degrees removes CO2, forming quicklime, which, when slaked with water, produces hydrated lime. This material hardened through carbonation, forming a durable lime plaster. Our experiment tested whether this process could produce plastic yet durable inlay material suitable for pottery decoration. Experiments were conducted both in real condition and in a controlled laboratory environment. Mollusk shells, animal bones, deer antlers, and human bones were used as a raw material. Throughout the process, we monitored temperature change, pulverization properties, and final inlay characteristics, including paste texture and color. The experimental inlays were analyzed using the same scientific methods as the archaeological samples to enable a direct comparative analysis of their composition and microtexture. The initial experiment was conducted in an open fire with short soaking time. Mollusk shells were placed inside a ceramic vessel, covered and placed in the center of the bonfire. After an hour, the firing process ended and the shells were removed while still hot. Shells remained whole, but when water was added, they quickly disintegrated into a thick grayish-white paste. After mixing, we obtained a homogeneous paste that was easy to apply to pre-fired pottery. After 24 hours, the material hardened into a durable lime plaster, keeping the inlay intact even after washing. In contrast, during the same experiment in real condition, the animal bone firing was unsuccessful. The bones did not calcify because of the short exposure to high temperatures. Therefore, we had to test bone material in more controlled conditions. We increased firing time, soaking duration, and temperature in a controlled setting and used different kind of bone material. After firing in laboratory kiln, bones were cooled and ground into powder, revealing differences in texture. Therefore, in some cases, sieving was required to obtain a finer powder. Once ground into powder, water was added slowly while mixing to create a homogeneous thick paste, which was then shaped into briquettes to test their strength. After 24 hours of drying, they hardened, demonstrating their potential for bone-based plaster material. The results showed clear differences in texture and color among the various bone-based materials. For example, human long bones produced fine white powder, while animal long bones and skull fragments were harder and yellowish. They required multiple sieving steps. Antler was the easiest to grind and homogenize, and it produced the whitest powder. By comparing the analysis of archaeological and experimental incrustation paste, microscopic analysis showed that the experimental shell-based plaster did not entirely match Copper Age inlays, which had a finer and more uniform structure. However, shell fragments shared similarities in shape and composition. Differences in optical properties suggest either a low firing temperature or incomplete carbonation of the lime. In contrast, the experimental antler and bone-based plasters closely resembled Bronze Age inlays. Both archaeological and experimental samples displayed fibrous microstructures with osteons, though experimental inlays show more pronounced firing effect, such as darker coloration and occasional vitrification. Infrared spectroscopy and X-ray diffraction confirm that experimental and archaeological bone-based plasters contain hydroxyapatite. On the other hand, shells fired at 800 degrees primarily contain calcite, matching some archaeological samples, while those fired at 400 degrees retained aragonite, also found in the archaeological samples. Analysis of prehistoric inlays from Croatia identified three main components: hydroxyapatite, aragonite, and calcite. Bone-based materials dominated the Bronze Age, while Copper Age samples show greater variability, incorporating mollusk shells. The presence of calcite in shell-based inlays indicates heating above 450 degrees. Some Copper Age samples preserved aragonite, suggesting lower firing temperatures or mixing of under-fired shell material with slaked lime. Experiments therefore confirm that both bone and shell material could be successfully transformed into durable plasters throughout thermal treatment above 700 degrees. Moreover, this process aligns with the principles of slaked lime technology, proving that prehistoric communities not only applied this method but also understood the transformative properties and benefits of heating and rehydrating specific raw materials. These findings provide the first direct experimental validation of prehistoric inlay making technique and offer compelling evidence that early artisans possessed sophisticated knowledge of material transformation process. Moreover, the production of inlays was likely intertwined with other crafts and social activities such as pottery firing, metallurgy, and funerary practices. The choice of inlay material may have been culturally significant. Bronze Age Pannonian communities consistently used bone, while Copper Age groups exhibited greater flexibility, incorporating mollusk shells. The preference for bone-based inlays in the Bronze Age coincided with the emergence of cremation as a widespread funerary practice. This connection could suggest a deeper cultural and symbolical significance of bone processing, extending beyond pottery decoration to broader ritual and technological shifts in prehistoric societies. Thank you for attention.